Hello everyone. Today I'm going to demonstrate examples from the chapter 7 of our microcontroller textbook. First, I will be demonstrating example 7.1 from the AVR microcontroller textbook. We will be coding a binary counter in C and simulating it using an ATmega2560 microcontroller in Proteus. Okay, so let's move on to the C program. So I have already written these programs in my FL Studio software. So let's look at the code I have written in C. First, there is hash define FCPU. Now, what this does is it tells the Proteus that the microcontroller frequency is set at 16 megahertz, and it also include an hash include delay.h library, so we can actually see the counting happen. In the main function, I use DDRB is equal to 0xFF. This sets the port B as output where your LEDs are connected. And it's also a crucial step. It tells a microcontroller that all the pins are on port B act as outputs. Next, I have used a while loop. Okay, I have used a while loop, and what will it do is that it will increment the variable z from 0 to 255. So basically, inside the while loop, we have used a for loop, right? So this is important. So it basically increment a variable z from 0 to 255 in every loop. The variable z is sent to port B. To make the simulation visible on camera on camera, I have added a 200 millisecond delay. So the code that was shown on the book, it didn't have a delay. So when I was running the simulation, the LEDs were blinking that fast that it didn't show as if they are blinking. They were just uh, like they are just constantly on. So in order to show the blinking, I have set a, delay. I have added this delay in this default code. Okay, so now I hope you understand the code. Now let's move on to our Proteus simulation. I have already designed the circuit. So in the Proteus, we have used LED bar graphs. So I have the ATmega2560 here, and I have connected an LED bar graph to port B, specifically pins from PB0 to PB7. Let me show you. So yes, from IO53 to IO13, which are equivalent to port PB0 to uh, PB7 or PB6. Yes, basically we have utilized the port B, and I have set the negative terminals, all of the negative terminals to the ground. And now instead of using 8 LEDs, I have used a whole LED bar graph assembly here, which is more easier to work with, and the wiring is also limited. So yeah, it's a much more easy way of doing things. So LED represents a binary digit. Each LED represents a binary digit. PB0 is the least significant bit, and PB7 is the most significant bit. The other side of the LED is connected to a common ground terminal, as we have shown. Now let's simulate it. Now I'll start the simulation now. Okay, let's start it. Okay, so as you are seeing that LEDs are basically blinking in a specific pattern. So LEDs aren't just moving one by one, they are adding up in the binary. The first LED blinks the fastest because it represents 1. When it turns off and the second LED turns on, that represents 2. When both are on, that represents a 3. So the random looking pattern is actually a perfect binary count from 0 to 255. This confirms that our software logic is controlling correctly the hardware pins. Now this example exercise shows how we can use the C programming to handle data and control external hardware via AVR ports. Thank you for watching. Basically, I will be adding all these examples in a single video. So this was our example 7.1 from the AVR microcontroller book, chapter 7. Now I will make a simulation for the second example, and I will also write the code for the second example. So till that, I will pause my recording and then start it again. Okay, now let's move on to the example 7.2. So where this example asks us to AVR C program that sends the hexadecimal hex values of the characters 0 through 5 and 0 through 5 and A through D to port B. So this is a fundamental exercise in understanding how microcontrollers translate human readable characters into binary signals that hardware can understand. Now let's move on to the code. So let's look at the implementation. Now let's move to the AVR studio. So okay, here is our code. Okay, let's start. So we include AVR IO.h to access the port registers. We define an array. We define an array. My list containing our characters. It's important to remember that microcontrollers don't see the letter A. It sees the hex values 0x41. So this is my list, and this is our hex characters, unsigned char Z. Now, let's move on to the main. So this is our main function. Okay. So we have set port B as output. DDRB is equal to 0xFF. So this command configures all 8 pins of the port B as outputs. Without this, our LEDs won't light up. Now, what we have done is we have used a while loop in which we have used a for loop. So in for loop, we have iterate through all 10 characters in our array. Each iteration port B is equal to my list sends the ASCII bit pattern of the specific characters directly to the physical pins of the chip. Now, why we have used while? Because it acts as a stop for the CPU, preventing it from restarting or executing random memory after the task is done. So I hope you have completely understood the code. It's a very basic code. So let's move on to our Proteus simulation for this program. So as I have illustrated in the first example, the Proteus is almost same as the example 7.1. So let me again revise what I have done. I have connected pins PB0 to PB7 to the input pins of the LED bar graph. On the other side, the bar graph is tied to a common ground. Here is our common ground. Now LSD to MSB, PB0 represents the least significant bit, which is the top LED, which is the IO53, where you can see here is IO50. 3, and the PB7 is the most significant bit, which is the bottom LED. In this case it is IO13. Where is IO13? So yeah, it is PB7. Now let's run the simulation. So when the simulation runs, the bar graph acts as a live binary monitor. For example, when the program sends 0, the LED will show 0011 and 000 in binary. So when it reaches A, the pattern shifts to 0100 0001. So basically, the lights LEDs will light up in a binary specific pattern. So let's execute it. Okay, now as you can see that this is the binary pattern, as I have said earlier. Since the code runs at the clock speed of the MCU, the transition happens instantly. So to see the sequence in a video, like I have added a delay in the code. I have added a specific delay in the code, so that's why you are seeing the blinking. So, and that's it. I think you have understood this example, and I think we should move to our example 7.3. Okay, let's move on to the example 7.3. So it's states that write an AVR C program to toggle all the bits of port B 200 times. So what does it means that our goal is to toggle all bits of port B exactly 200 times, and this is basically an exercise for understanding how can we manipulate the hardware states using C's bitwise operators. Okay, let's move on to the AVR code. So I have already written the code. So here, as previously stated, we are using the standard libraries here, AVR IO.h, AVR IO.h, and the CPU has a 1 megahertz clock. So we have also used this delay headed file so that we can see the delays between LEDs blinking in our simulation. Now we have set DDRB is equal to 0x SR. This means that the port B here acts as an outputs. Now port B is the output. Then we initiate port B to 0xAA. Okay, so now this is a very important point. This is the initial pattern. So why 0xAA? 0xAA is basically 10101010. This creates a pattern where every other LED on our bar graph starts in the on position. So the toggle logic inside our for loop, we use the statement. Where is the for loop? Okay, here is the for loop. So what we have done is we have used the statement port B is equal to negation of port B here. So this, what will this do? This will toggle all bits. This will toggle all bits. So now this is the operator you see here. This is the bitwise not operator. It flips every 0 to 1 and every 1 to 0. Now by running this loop 200 times, so we are basically running it 200 times. What will happen is the LEDs will swap places repeatedly, creating a flashing effect. Now, I hope so you understood the hardware. Sorry, not the hardware, the code correctly. So now let's move on to the Proteus simulation for this circuit. So the setup is same. So I have used an ATmega2560 microcontroller. We have used an 8 LED bar graph. We have connected all the LEDs from PB0 to PB7 in the bar graph, and the common side is the ground. So these all are connected to a common ground, and this LEDs are basically connected to port B PB0 to PB7, IO53 to IO13. Here I usually use the default connection instead of just manually connecting the wires to the pins. This method is very easy because you don't get jumbled up in complex wiring. Okay, so now now what will happen when I will simulate this? So in the chip settings, I have matched the clock frequency to the F CPU defined by my code, which is 1 megahertz to ensure the delay timing is accurate. So the result. Now when I play the button, okay, let's play it. Okay, so this is the pattern that we should observe. So you can see the check port pattern instantly flipping. The LEDs that were on, they go off and vice versa. It will perform this swap every 200 times before coming to a stop at a while command. So I hope you understood this binary pattern here, bitwise toggle switching. It is also known as bitwise switching. Okay, so simple toggle logic is used in everything from blinking status LEDs to generating square waves for communication protocols. Have you found this explanation helpful? Uh, if you found this explanation helpful, I hope you can understand the whole concept here. So let's move on to the next example. I hope you understood the code and the hardware perfectly. Let's move on to the next example. Okay, so now let's move on to the next example, which is our example 7.9 of the AVR microcontroller book. So what the example asks us is to LEDs are connected to the pins of port B. So write an AVR C program that shows the count from 0 to FF on the LEDs in binary. Okay, so we are basically going to build a functional 8-bit binary counter using the AVR microcontroller. We will be writing a program that counts from 0 to 255, which is from 00 to 0xFF, and display the count in real time on an LED bar graph. Now let's move on to the code that I have written. So we have defined FCPU as 1 megahertz. So the CPU frequency is here I am using is a standard 1 megahertz clock for the simulation. Now the important thing is that to match the clock in this Atmos Studio and Proteus, I have also made changes in my Proteus ATmega2560, where I have set the clock frequency to 1 megahertz also, where the default frequency is 16 megahertz. So okay. Now let's move on to the code again. So this was the important thing to tell you. So now uh, we have used the delay header file here because without a delay, the microcontroller would count 0 to 255 so fast that the LEDs would just look like they are all turned on at once. So next thing is we do is we set DDRB is equal to 0xFF. We set all the pins of the port B as the output pin. That tells the ATmega2560 microcontroller that all the 8 pins on the port B are the output pins. So inside our while loop, we have the heart of the program, which is port B is equal to port B plus 1. This is the this increment the binary values on port B. At every time this line runs, the binary value in the port B register increases by 1. After a 500 millisecond delay, it loops back once the counter hits 1, 1, 1, 1, 1, 1, 1. The next increment naturally overflows the 8-bit register, resetting back to 0, 0, 0, 0, 0, 0, 0, 0 automatically. Oh, so I hope, and we have then at the end, the code has ended via return 0. So let's move on to the Proteus simulation here. Now the hardware is same, so we have used our ATmega2560 chip and an LED bar graph. LED bar graph. So we have connected LEDs, these LEDs from 1 to 7 uh, with the port B from PB0 here. This is the PB0. Wait. Okay, this is the PB0, which is labeled as IO53, which is the least significant bit to the top, to the most significant bit, which is PB7 over here. And PB7 is what? Let me check. PB7 is IO13. So then we have done the grounding. We have connected all the negatives to one single ground here. Okay, now we what we will do is we will set the clock frequency here to 1 megahertz, which I have already done. I have set it to 1 megahertz. The default is 16 megahertz. Now let's hit the play button. Okay, now I have. Okay, so this is the simulation. So what's happening here? Watch the top LED, the PB0. It represents 2 to the power 0. It toggles on every single count. The second LED is PB1, represents 2 to the power 1 and toggle every 2 counts. The pattern continues down line by line. This line, the time the bottom LED PB7 turns on, you know the counter has reached at least 128. Okay, so this is the perfect way to visualize how data increments inside a computer's CPU. Okay, so I hope that you understood the example. Now we will move on to our next example. Okay, now let's move on to our example 711. So it says that write an AVR C program to get a byte of data from the port C. If it is less than 100, send it to port B. Otherwise, send it to port D. Okay, so what are we trying to do here? We are basically using conditional I/O routing. We'll be using the ATmega2560 microcontroller to read an 8-bit value from a set of logic toggles and decide based on that value where to send the data. This is how microcontroller makes decision based on the physical input. So basically this example is related to the decision making of our microcontroller. So let's move on to the code and let us explain the logic over here, what's happening in the code. So we have set the DDRC port equal to 0. DDRC port is set to 0. So port C is listening to our toggles, and DDRB and DDRD are also set to so DDRC is set to input, and DDRB and D are basically set to the output ports. This B port is for bar graph 1, and this D port is basically for the bar graph 2, the decision. Now in our while loop, we read the toggles using temp is equal to PINC. So we are basically reading the toggles using temp is equal to PINC, which reads the toggles. Now we've set a threshold of 100 if the toggles represent a number less than 100. If the toggles represent a numbers less than 100, the data goes to the port B. The data will go to the port B. Otherwise, if they represent 100 or more, the data will jump to the port D as it is shown in our loop. So I hope the code is very easy. So I think we should move to the Proteus hardware setup. Okay, so this is a very interesting uh, setup we have done here. So what we have done is that the stars showed are there are we are using the 8 logic toggles which are connected to port C. So we have connected each logic toggle. There are total 1, 2, 3, 4, 5, 6, 7, 8 logic toggles, and I have connected them directly with the port C. As it is expressed here that this is the PC0 pin and this is the PC7 pin. So from IO37 to IO30. So from IO37 to what? IO30. Okay. Now, each toggle represents one bit of a binary number. PC0 is our least significant bit. So this is our least significant bit, which means what? 2 to the power 0 is equal to what? 1. And PC7 is our most significant bit, which will be what? It will be 2 to the power 7, and I think it is equal to what? So 2 to the 7, 2 to the power 7 is okay, 128. So by switching these from blue to red, we can input any decimal number from 0 to 255. For our outputs, we have two LED bar graphs. Okay, so here we will basically make input at the port C and at port B. This is my first LED bar graph, which I have connected with the port B, which is from IO53 to IO13. Let's check whether it is port B or not. So yes, from IO53 PB0 to PB7, which is IO13, I have connected this first LED bar graph with the port B. So the second bar graph. Here is the second bar graph, which I have connected with port D from IO21 to IO38. Port D from IO21, here from IO21 to IO38. So I think the components are clear. It's very simple. An ATmega2560 microcontroller, 8 input toggles which are connected with port C, an LED, two LED bar graphs that acts as output. One LED bar graph is connected with port B and the other LED bar graph is connected with the port D. So now the code logic we have already explained. So now we will live demonstrate what happens when I hit the play button. Okay, now let's do this stepwise. Okay, I hit the play button. Now, let's talk about the scenario one where we will use below 100 logic. Currently, all the toggles are set to 0. If I flip the toggles for PC 0, okay, so let's start flipping. So PC 0, okay, this is PC 0, which is IO37. Let's flip it. Okay, now it is flipped to 1. Now let's move on to PC 0, PC 1, 2, and 3. IO34. So let's also flip the IO34, which is the PC3 toggle and the PC5 toggle. So this is our PC5 toggle, which is IO32. Let me recheck. So yes, PC5 is where it is. Here it is. Here it is. So yes, PC5 is on. So what's happening over here? What's happening? You see the port B bar graph. So this is our port B bar graph, and it has lightened up. The microcontroller sees that 41 is less than 100 and routes the digital signal accordingly. Port D remains completely dark. So here port B lights up and D remains completely dark. Now let's move on to the scenario 2 where we will cross the threshold. Now let's cross that 100 mark. What will I do? I will let me reset all the toggles over here. Okay, let's reset all the toggles and we will try something new. Okay, now let's try something new. So I'll toggle PC6. So PC0, PC1, PC2, PC3, PC4, PC5, and PC6. Here is PC6. Let's toggle it. Okay, PC6 is toggled. Then I will toggle PC5. So this is PC5. I have toggled my PC5. Now this gives us a 96 still on port B. But the moment I click on PC2, here is PC2 0 1 2. This is PC2. Let's toggle this. Bring out now. We are on a total 100. Now let's look at the bar graph. The data instantly vanishes from port B and appears on the port D. Okay. So here, after having this scenario, we are exactly equal to 100. So port B is completely off and the data is on port D. Now this jump happens because the else condition in our code C has been triggered. ATmega2560 is polling these toggles thousands of times per second, making the transition feel instantaneous. So I hope you understood everything. So this is how our logic toggles to interact with branching code on an ATmega2560. Whether you are building a sensor, a monitor, or a control system, mastering this conditional routing is essential. I hope that now the concept of toggling is clear, and I hope you understood all the previous examples that we discussed in this video lecture. So thank you very much for watching.